Let's look at impulse and momentum. There's two different concepts that we'll see that they are related. So first, let's look at impulse. We say that force gives an object a certain impulse when it acts on that object for a certain amount of time, delta t. So I have impulse, the unit is, the symbol is capital J, is the average force that acts on an object for a certain amount of time, delta t. Just like force, impulse is a vector, so it will act in the same direction as that average force. So let's look at some examples. If we have an egg up here that we're going to drop on a t-shirt, and then later on we're going to have an egg that we're going to drop on a hard surface. So let's see what happens. There's the egg dropping on the t-shirt, and you notice that the egg didn't break. It was in contact with the t-shirt for quite a long amount of time, but it didn't break. In the second example, we have the egg colliding with the cutting board, and it was in contact with the board for a very short time when it first touched the board. And that's why the force of impact was larger in the second example than in the first example. We know that the weight of the object of the egg was what pulled it down. So we would assume that the average force was the same in both situations, but that is not the case. We're not looking at the force that the egg has. We look at the force with which the egg impacts the t-shirt or this hard surface, and that force is not a constant. So in the instance with the hard surface, the first molecule of eggshell touched the surface, and it was a very quick collision with that hard surface, and that quick amount of time, delta t, gave us a large force that broke the egg. In this other instance, when the egg collided with a t-shirt, the t-shirt molded itself around the egg for a longer period of time, and that meant that the force of impact was distributed over a larger amount of time, and the egg didn't break. The impulse is measured in newtons times seconds. It's the unit for force times the unit of time. Then the second concept, momentum, is P is the symbol for momentum, is mass times velocity. So any object that is moving with a certain velocity v will have a momentum. Momentum is a vector since it is the product of a scalar quantity and a vector. So momentum and velocity will be in the same direction. The units for momentum are kilogram meter per second because the unit of mass is the kilogram and the unit of velocity is meter per second. So that's where we get this from. Now let's do a little calculation here. Let's start out with impulse is equal to average force times delta t, and I'm going to rewrite average force as mass times acceleration, average times delta t. So impulse is mass, average acceleration is delta v divided by delta t, and we multiply that by delta t. So if I cancel these two out, I end up with impulse being m delta v, or I can also call this delta p. So I notice that impulse is actually change in momentum. And when I wrote out the units for impulse and momentum, I wrote them out based on the definitions of the different quantities. But actually, if we remember that a Newton is a kilogram meter per second squared, and that we multiply by the second, then we end up with kilogram meter per second for impulse, which is the unit for momentum as well. So we have a new relationship here between the impulse and momentum, and that is called the impulse momentum theorem. So here we have it summarized. The impulse momentum theorem says that impulse is actually change in momentum. Now, momentum is a very special quantity. Just like energy, momentum is conserved. And we say that in the absence of external forces, the momentum of a system before a collision equals the momentum of a system after a collision. So what are collisions? Well, whenever two things come in contact with one another, when they collide, we say that the momentum before that collision is going to be equal to the momentum of the system after the collision. There are different types of collisions, and the first one that we're going to look at is what we call an inelastic collision. And in an inelastic collision, momentum is conserved. So here we have a little example. We have this person running, and let's say that the person has a velocity v initial, and there is a cart here, and let's say that the initial velocity of the cart is 0. Let's say that the person has a mass m1. Let's say that the cart has a mass m2. So this is what's happening before the person jumps in the cart. So we will say that this is the before the collision. Then over here, after the collision, the person jumped into the cart, and as a result of this, the system is going to be moving with some final velocity. So we'll say that the momentum before the collision equals momentum after the collision. And I picked this to be a one-dimensional problem because everything is simpler that way, and I can get rid of the vector symbols then. So the momentum before the collision would be the momentum of the person plus the momentum of the car or cart before, and that's equal to momentum of the person plus momentum of the cart after the collision. So momentum of the person before the collision would be mass of the person times the initial velocity. The cart was not moving before the collision, so I have mass 2 times 0. That's the velocity that I picked for it. And then after the collision, we have the person moving with velocity v final and the cart moving with velocity v final as well. So mass 1 v initial is going to be equal to mass 1 plus mass 2 times v final. So this is an example of an inelastic collision. I don't know what we would be looking for in this particular problem. Let's say that we want to know the final velocity of the person and cart. So that would just be m1 v initial divided by m1 plus m2. So this would be the answer that we would get for this inelastic collision problem. Now, another type of collision is an elastic collision. And in the case of an elastic collision, momentum and kinetic energy are conserved. Elastic collisions are actually very few. We can say that molecules in gases collide elastically, or that in a particle accelerator there is an elastic collision. But usually all collisions, or most collisions, have some sort of loss of energy. And that's why we cannot say that most collisions are elastic. Most of them are inelastic, but in rare occasions we can assume that there is an elastic collision. So let's pretend that we're dealing with an elastic collision here. So I'm going to say that ball 1, let's say that the red ball has mass 1, let's say that the blue ball has mass 2. So m1 has velocity 1 initial, and let's say that the velocity of ball 2 initial is 0. I'm going to simplify things as much as I can. Here is where the two balls collide, and after the collision, let's say that the mass 1, the red ball, has a velocity v1 final, and let's say that the blue ball has V2 final. So these are the things that we're going to assume in the problem. So we know that momentum and kinetic energy are conserved. So I'll write here kinetic energy initial equals kinetic energy final. So I'll have 1/2 mass 1 V initial 1 squared plus 0. I made the velocity of the second ball 0 initially. That is equal to kinetic energy of the first ball after the collision, so that's 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. So this would be our conservation of kinetic energy equation. Then we also know that momentum is conserved. So I have momentum before the collision is equal to momentum after the collision. I made this one-dimensional so that I can keep the momenta as scalars rather than vectors. I'm going to get rid of the vector symbol over that. So now when I write the conservation of momentum, I have before the collision mass 1 times V initial 1 plus 0 is equal to mass 1 V1 final plus mass 2 V2 final. So I have these two equations and I have two unknowns. I'm looking for the velocity after the collision. So I'm going to star this equation and I'm going to double star the second equation so that I can keep track of the different equations. And now from the second equation, from the double star equation, I'm going to solve for V1 final. So V1 final will be M1 V initial 1 minus M2 V2 final divided by mass 1. Then I'm going to call this equation triple star. Now if I substitute the triple star equation into the one star equation, then I have 1/2 m1 v initial 1 squared plus 1/2 m1, and now I'm substituting the v1 final, so I have m1 v initial 1 minus m2 v2 final divided by m1 quantity squared plus 1/2 m2 v2 final squared. And now I'm going to have to do some solving. How about I get rid of all of the 1/2s, and actually this is supposed to be equal right here. So I'm going to cancel all the 1/2s and I'm going to say that m1 v initial 1 squared is equal to, I have m1 here and m1 squared there. So I'll cancel this one out and just have m1 on the bottom here. So I'll do m1 squared v initial 1 squared minus 2 m1 v initial 1 m2 v2 final plus m2 v2 final, both of those squared, divided by m1 plus m2 v2 final squared. So let's rewrite this. So m1 v initial 1 squared equals, I can divide m1 squared by m1 and have m1 v initial 1 squared minus, here again I can divide m1, So I have minus 2 V initial 1 M2 V2 final plus M2 squared over M1 V2 final squared plus M2 V2 final squared. And I notice that I can cancel out M1 V initial 1 squared. And from that, I'm going to factor out V2 final. So now I have 0 on the left side, and that's equal to V2 final times negative 2 V initial 1 M2 plus M2 over M1. I had M2 squared divided by M1 times V2 final, because I factored out one V2 final, but this is V2 final squared, plus M2 V2 final. And the only way that this product between V2 final and this mess over here can be 0 is if either V2 final is 0 or if this mess here is 0. So this is true for V2 final being equal to 0, or I'm going to factor out the V2 final in this second expression right here, or V2 final is equal to 2M1 V initial 1 divided by M1 plus M2. So I solved for velocity 2 final in terms of the initial velocity of the first ball. Now, I know that V1 final, where was that? V1 final from here is a function of V2 final. So I can plug in this in there, and when I do the math, I'm not going to do it here because I don't have much room. I end up with V1 final is V1, the initial one, sorry, plus times, sorry, M1 minus M2 divided by M1 plus M2. So you see that this is a really messy situation where you have to do elastic collisions. And I actually simplified this quite a bit, where I set the velocity of the second ball equal to 0, and I made it a one-dimensional collision, and still I had so much to write, and I also skipped a few steps so that I can get to the answer faster. So elastic collisions are very, very messy. So now the next concept is that of center of mass. And we'll say that the center of mass is the point that represents the average location for the total mass of a system. So far, in all of the problems that we've dealt with before, we looked at objects as if they were point masses. We assumed that their masses were concentrated at a single point, and that's what we call the center of mass. From now on, we're going to actually use macroscopic objects, so we're not going to just consider a block being a point. We will look at how the objects are structured in future lectures. So to find that special point, that center of mass, we can use these equations. So we have the x center of mass, the position of the center of mass is the sum of the mass of part of the entire mass times its center of mass plus mass 2 times its center of mass divided by the sum of those masses. So what do I mean by that? Let's say that I have an object that looks somewhat like this, and I want to find the center of mass for it. I'm going to place this at the origin of a coordinate system. So this is my x and my y. And for these types of objects, very regular objects, I know that the center of mass of a rectangle like this would be right here. I know that the center of mass of this rectangle would be right there. So this would be my x1, this would be my x2, and similarly, I would have this as my y1 and this as my y2. So in the equation, what I mean is that I can multiply the center of mass in the x direction, so this distance times this entire mass, plus this distance, this is the center of mass of the second portion of this, times the mass of this block divided by the sum of the masses, so the mass of this entire thing, and find the center of mass of the object in the x direction. I do the same thing in the y direction, where now I multiply this distance, y1, times this mass, plus y2 times this mass, and then divide by the entire mass of this blob here. And that gives me the y of the center of mass. Now, another concept that is very useful is that of the velocity of the center of mass. And it's very similar to what we have had here. We're going to look at how an object moves about its center of mass. And this is a fascinating thing to think about when you're looking at fireworks. You have one rocket that starts from ground level, and that rocket is being shot on a parabolic path that would go somewhat like this. But somewhere this rocket is going to explode in different chunks. So one chunk's going to go that way, another chunk's going to go that way, and there's lots and lots of chunks, but I'm only going to look at all these 4 chunks. And each one of these pieces of the rocket has a velocity. So this is velocity 1, this is velocity 2, velocity 3, velocity 4. And it turns out that if you try to find the velocity of the center of mass, what actually happens is all of these different pieces of the rocket will move in such a way that the center of mass of the rocket continues on its parabolic path. So it doesn't matter that the rocket just broke up in so many pieces. All of the motion of all these pieces is going to continue so that the center of mass of the rocket will continue on the parabolic path.